Percent yield is something that we often calculate in the organic chemistry lab when we do a synthesis experiment. So that is an experiment where we are transforming one or more starting materials into a new product. And percent yield is then a way of expressing how efficient was that synthesis? What percentage of the maximum yield did you get? So when we are calculating a percent yield, we need to look at the chemical equation and we need to determine, and also the amount of starting materials that we've been given to determine what is our mole ratio. So from 1 mole of product, how many, or 1 mole of starting material, how many moles of product do we expect to form? If we are given amounts of more than one starting material, we need to check and see if we have a limiting reactant. Is there one reactant that is present in a lesser amount compared by moles that will run out and limit the amount of product that we can form? And so from our mole ratio and our limiting reactant, we can calculate a theoretical yield. So your theoretical yield is the maximum amount of product that can form if this reaction goes to completion. And so that is a number that you'd want to have probably before you start the lab experiment. So you have an idea when you go and you get your final mass of product, how efficient that experiment was. And the way that we express this is as a percentage. So your theoretical yield, that's that maximum amount that you can possibly form. So we put that here in our calculation. And your experimental or actual yield is the amount that you actually measure when you are done your experiment. So let's take a look at an example. So here we have an example of an esterification reaction where we are reacting benzoic acid and methanol to form methyl benzoate, and we have water as a byproduct. So this is our balanced chemical equation. It might look a little bit different than what you're used to seeing in general chemistry. So in general chemistry, you often saw molecular formulas in your balanced chemical equation. And here we are showing structures. And it's very common in organic chemistry to show the structures in a balanced chemical equation. We can still look at this and examine what we're given to figure out the mole ratio. So one thing we will notice is we don't have any stoichiometric coefficients. So that usually implies that you've got a 1-to-1 mole ratio. We can also look at the structure. So we can see from the benzoic acid that we have a benzene ring, and then we have the carboxylic acid portion. And we can look over at our methyl benzoate, and we can see, well, we're incorporating one benzene ring and one carbonyl, carbon-oxygen double bond. So it looks like we're using 1 unit of benzoic acid. And if we look at the methanol, we see this OCH3 and this OCH3. So it looks like we're incorporating 1 methanol unit when we're making this methyl benzoate. So we have a 1-to-1-to-1 mole ratio. So with that information, we can look at the rest of the information that we're given. So we're told that a student reacts 5 grams of benzoic acid with 5 milliliters of methanol and obtains 5.10 grams of methyl benzoate. So we are given the actual yield here. What we need to do to get to the percent yield is we need to look at these two amounts, determine which one of those reagents is the limiting reactant. From that limiting reactant, get the theoretical yield, and then we're going to use the actual yield and the theoretical yield to calculate the percent yield. So to compare amounts, we need to compare in moles. So we need to do some unit conversions. So our benzoic acid, we're told we measured 5 grams. And if we look at the benzoic acid and the information we're given, benzoic acid, we were given a melting point. So this implies that benzoic acid is a solid at room temperature. So it makes sense that we're measuring this in grams. So to get to moles, we need to take that 5 grams and use the formula weight of the benzoic acid to calculate how many moles we had. And from our balanced chemical equation, 1 mole of benzoic acid should give us 1 mole of methyl benzoate. With our methanol, we see that we're being given a boiling point. So this implies that the methanol is a liquid at room temperature. And so we are measuring that by volume, which is typical for liquids. So we need an extra conversion step here. So we have our volume, we need the density of that liquid, which is given right here. So this tells us that 1 milliliter weighs 0.791 grams. So we take the volume in milliliters, use the density to convert to grams, then use the formula weight to convert from grams to moles. And again, we have a 1-to-1 mole ratio between this reactant and the methyl benzoate product. So to determine the limiting reactant and the theoretical yield, there's a lot of different ways that you can approach this. So as long as you get to the same answer and you show your calculation with the units, that's fine. I like to take each one of my starting materials and just line up all my units and say, if benzoic acid starting material was the limiting reactant, what would be the theoretical yield of methyl benzoate? And then I'll do the same thing with the methanol. Whichever one of these calculations gives us the lower yield of product, then we know that's the one that's limiting the reaction, and then that's the theoretical yield. So with the benzoic acid, we were given 5 grams. So we use the formula weight to convert grams to moles of benzoic acid. The mole-to-mole ratio from the balance equation is here. We know that 1 mole of benzoic acid forms 1 mole of methyl benzoate. And so this would give us the amount, the theoretical yield at this step, if we stopped here, would be the theoretical yield in moles, which you can certainly compare in moles. We're going to do one more conversion here, though, to get grams. So once we have moles of methyl benzoate, we use the formula weight of methyl benzoate to get the grams of product. Pay attention to significant digits. It's limited by this initial starting mass. We had 3 sig figs here, and all of our conversions are multiplications and divisions, so we keep that smaller amount of sig figs, which is 3, so we still have 3 here in the product. So if benzoic acid is the limiting reactant, then this would be the theoretical yield. Let's check our other reagent, the methanol. So we're going to calculate from the amount of methanol how much benzoic acid or methyl benzoate could be formed. So we started with 5 milliliters of methanol. We used the density. So this tells us what 1 milliliter of methanol weighs. So we can go from milliliters to grams of methanol. And then we use the formula weight lined up so that grams cancel so that we get the moles of methanol. We use the mole ratio from the balanced chemical equation. So we know that 1 mole of methanol would form 1 mole of methyl benzoate. And then we use the formula weight of methyl benzoate to get the theoretical yield. And again, we paid attention to significant digits. We had 3 in our starting volume. So we have 3 in this theoretical yield. And we can see that the methanol could potentially form a lot more methyl benzoate. So that means that this is present in excess. So that tells us that the benzoic acid is our limiting reactant, and this is our theoretical yield, the 5.57 grams. And so now we're just one step away from our percent yield calculation. So the percent yield, remember, is what percentage of that theoretical yield did you make? So the theoretical yield is what we just calculated on the previous slide, and this experimental or actual yield was given in the original problem. If you're doing this yourself in the synthetic lab, that's going to be what you weigh at the end of the experiment. So we can see that our theoretical yield, we put that on the bottom, the 5.57 grams. The problem told us that we made 5.10 grams, and so that gives us a percent yield of 91.6.